Chapter 2 has to do with chemistry and the chemistry of the human body and how it relates to life. So if you think back to the levels of organization, atoms making up molecules, that foundation is going to have a major influence on everything above it. So the way chemistry works is going to matter. So let's start with the idea of atoms and what atoms are. So atoms are things like carbon, hydrogen, oxygen, nitrogen, phosphorus. The K stands for potassium. The S stands for sulfur. The Na stands for sodium. Ca for calcium. Mg for magnesium. Cl for chlorine. And those are some of the main atoms. Those atoms together, when you've got a bunch of the same atom together that makes up an element, we would say that's elemental carbon. It's a whole bunch of carbons together. As you can see my picture here, that a whole bunch of carbons together, we call that graphite, pencil lead. So if you've ever been stabbed with a pencil before in your past, don't worry, it's not lead poisoning because lead is a heavy metal, like lead pipes. This carbon or graphite in a pencil, we sometimes call it pencil lead, but it's really graphite. But carbon is useful for organic molecules. Most organic molecules have carbon, hydrogen, and oxygen in them. And a lot of it has to do with their chemical structure and the way they bond together for things. Oxygen is especially helpful for things like cellular respiration, whereas nitrogen in the human body, we see that a lot in proteins and DNA. Phosphorus is going to be significant also for DNA, but in energy molecules. And then potassium has a lot to do with muscle and nerve function. Sodium and sulfur. Sodium is useful for water balance. Sulfur, the S, that's useful for making proteins. Calcium for bone strength, magnesium for blood, and chlorine for things like water and fluid balance. Here's a picture of an atom. The nucleus of the atom consists of protons, neutrons, and electrons. The protons are positively charged, that's the C. The neutrons have no charge, that's the B. The electrons that orbit the nucleus, that's the A. And you'll notice that the number of electrons, A, is equal to the number of protons, C. So protons, positive, electrons, negative, neutrons, no charge. And so long as the protons number matches the electron number, the atom is neutral, no charge. An ion has a different number of electrons. So the number of electrons can change. That makes the atom either positively charged if you remove electrons, or negatively charged if you add additional electrons. An isotope is where you have a different number of neutrons. So right now I've got 4 protons and I've got 5 neutrons. That would make this an isotope. Notice we can't change the number of protons, because by changing the number of protons, we're going to change the atom from one atom to a different one. So for example, carbon is carbon because it has 6 protons. Oxygen is oxygen because it has 8 protons. So let's take a look. If you look at a periodic table, you'll see elements listed like this with an atomic number. That's the number on top. The atomic number is the number of protons. So hydrogen has 1, oxygen has 8, carbon has 6. So what's the bottom number? The bottom number is the weight of the atom, the atomic mass. Well, how do you get that number? So the atomic number is the number of protons plus the number of neutrons. So to get the atomic number, you're going to take protons plus neutrons equals the atomic number. So if you're looking at carbon, there's 6 protons, 6 neutrons for a total of 12. If you look at oxygen, the number of protons is 8. So use a little algebra. The atomic weight is 16. So 8 plus what equals 16? 8 plus N equals 16. 8 plus 8. So there's 8 neutrons. Hydrogen is a little weird because there are no neutrons. 1 plus 0 is 1. So here's an example of an atom. Notice that it has 6 electrons. So if it has 6 electrons, it probably has 6 protons. You'll notice that the first energy level can only fit 2 electrons, and then the electrons have to be distributed in the next energy level. That energy level will be filled when there's 8 electrons in that level, and then the next level will be filled when there's 8 electrons in that level. Atoms then are going to form chemical bonds, and they do this for stability. All right, stability means that the outer energy level is full. So whether that's 2 if you're a really small atom, or whether that's 8 if you're a much larger atom, if those outer energy levels are full, then that atom is stable. So you'll notice with sodium, it only has 1 electron in the outer energy level. That's very unstable. Chlorine is missing 1 electron from the outer energy level. So sodium can give chlorine that extra electron so that both outer energy levels are filled, and when that happens, it forms a bond. In this case, it's an ionic bond. Why is it an ionic bond? Because when that electron leaves the sodium and binds to the chlorine, that creates an ion. Ions are where you have a positively charged atom or a negatively charged atom. And the way we get that positive or negative charge is by losing an electron or gaining one. So sodium has lost an electron, it's positive. Chlorine has gained an electron, so it's gained a negative. That's what makes chlorine negative. Sometimes atoms just share electrons to get those full outer energy levels. So you'll notice this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. And you're right, I'm counting those electrons twice because they're sharing it. That makes it a covalent bond. Covalent, co means to share. So both of these atoms are sharing electrons. When atoms share electrons, it creates a very strong bond. Right? A very strong bond. So covalent bonds are typically stronger than ionic bonds, where ions are being formed. Water is an example of a covalent bond. So here we have oxygen sharing electrons with hydrogen so that the outer energy levels are full. All right, so the chemical formula for water is H2O. What that means is this makes a molecule. And in the molecule, I have 2 hydrogen atoms, and I have 1 oxygen atom. Now, if I needed to calculate the molecular weight, I would take the atomic mass of hydrogen, multiply it by 2, because I have 2 of them. And I would take the atomic mass of oxygen. It's going to be 16, so I'm going to add those 2 together. So 16 plus 2, the molecular weight for this would be 18. So we can see there's 2 hydrogen atoms, 1 oxygen atom in that molecule. And if we add it together, we can get the molecular weight. Because oxygen has more protons positive, the electrons will spend a lot of time around the oxygen atom. That makes this molecule polar. Polar means it has a positive end on one side and it has a negative end on the other side. Because one side of the molecule is slightly positive and the other side is slightly negative, sometimes those positives and negatives attract and they form a little attraction. Those are called hydrogen bonds. So that's represented by the dotted line in between those water molecules in my picture. So when we think about a chemical reaction, this is how we get chemical energy. So it's stored in chemical bonds, either ionic bonds or covalent bonds. That's where we store the chemical energy. Mechanical energy is stored in more physical systems. So like your muscles or your bones are going to be using more mechanical energy to move things around. There's more than one type of chemical reaction. All right, so a chemical reaction consists of the reactants, what I put in, and the product, what I get out. One of those is called a synthesis reaction. I bring 2 things together. They make a new, bigger molecule. A decomposition reaction means I take a bigger molecule, I break it into smaller things, And an exchange reaction where I'm trading some of the things with other things. So some of those atoms are going to be traded around with other atoms. An exchange reaction. So here's an example of a synthesis reaction. We take amino acids to make a protein. We're building something bigger. Decomposition reaction, we eat something like starch and we decompose it into glucose molecules. An exchange reaction, here's a great example of an exchange reaction where I'm just switching some of those reactants around. The rate of chemical reactions matters, and there's different things that influence the rate of a chemical reaction. For example, some of the properties of the reactant, like if that reactant has a lot of surface area, well then it can often react much quicker or more violently. An increase in temperature can speed up chemical reactions to a certain degree. Definitely an increase in concentration or pressure will speed up chemical reactions. And if I have a chemical reaction that doesn't often work, what we can do is add an enzyme or a catalyst, and a catalyst can help get that reaction started. So think of it like this graph right here. The energy that the reaction normally takes is represented by this black line. That's an enormous amount of energy to get that chemical reaction to happen. So it doesn't happen too often. If I had a catalyst or an enzyme, which is a protein, enzymes are proteins, that lowers the energy required to get that chemical reaction to happen. So it happens much, much faster. A lot of times in the human body, chemical reactions cannot happen without the presence of certain enzymes. Well, in the human body, there are organic substances and inorganic substances. Carbon is foundational to organic substances, whereas inorganic substances are normally simple molecules that don't have much in the way of carbon. Water is a great example of an inorganic substance. Your body is made of 67 to 70% water. Water has a very high heat capacity. That is, it stores a lot of heat. It also helps to maintain your body temperature. When water evaporates, it has a high evaporation temperature, which means it takes a lot of heat for water to evaporate. And we use water to break things down. That's what I mean by the body's chief solvent. To summarize some of these characteristics of water, think of the acronym CR class. CR stands for chemical reactions because water helps facilitate some chemical reactions. Water can help cushion. It can help lubricate. It's a solvent. It dissolves things. And it has a high specific heat, which means it heats up very slowly, cools down very slowly. When we think of water as a universal solvent, what we mean is that it dissolves things. The reason that's important is because anytime we take a solute, like salt or sugar, it can dissolve in water because water is a solvent. If we increase the amount of solute, we can increase the concentration of the solution. If we increase the amount of solvent, then we're diluting the solution. Here's a great example of a reaction that's a synthesis reaction. We're bringing two things together. So we have a glucose molecule. The chemical formula is C6H12O6. We add it to another glucose molecule, C6H12O6. And together we get a maltose molecule. All right, so that's a great example of a synthesis reaction. But you'll notice something odd. 6 carbons plus 6 carbons is 12. 12 hydrogens plus 12 hydrogens, how does that equal 22? And 6 oxygens plus 6 oxygens, how does that equal 11? Well, that's because we've lost something. We've lost 2 H's and 1 O. That is called dehydration synthesis. So we put it together, synthesis, but we lose water, dehydration. There's a lot of organic reactions that are dehydration synthesis. We put the molecule together, but we lose water in the process. Often, whenever we are dealing with inorganic molecules and we have a decomposition reaction, and in that reaction, we release a hydrogen ion in the water, the solvent, water, that makes it an acid. So electrolytes are whenever we're making ions, and acids are definitely ions because they're losing hydrogens, and we're creating these hydrogen ions, which is what makes them electrolytes. So electrolytes are just whenever we have ions forming, or we're breaking down these bonds. And the reason they're called electrolytes is because they can carry an electrical impulse. So acids have a high concentration of hydrogen ions. We can measure that. Acids have a high concentration of hydrogen ions. We can measure that with something called pH. So the pH scale measures the relative concentration of hydrogens. 0 to 6 makes it an acid. All right, acids typically taste sour, and they react very strongly with metals. And if you get an acid on your skin, it will burn. So the more acidic is the lower the pH. So low pH numbers, very acidic. So for example, hydrochloric acid has a pH of like 0 or 1. It's very, very low. Why? There's a high concentration of hydrogen ions in that solution. A base is different because a base increases OH ions, still an electrolyte, but has a very low hydrogen concentration because the hydrogens are joined up with a oxygen, but they still are ions. Bases are measured on the pH scale from 8 to 14. A 14 is a very strong base, like oven cleaner, and they kind of taste bitter, so typically, and they're slippery like soap. But strong bases burn skin just like strong acids burn skin. So the closer we get to 14, the higher the OH concentration, the stronger the base. So right in the middle is 7. That's water. It's neutral. Why? Because it has the acid amount is equal to the base amount. The H's are equal to the OH's. Here's an example of some things that you would find on the pH scale. Notice again that water right in the middle has an equal number of hydrogen ions as it does OH ions. So you'll notice some things like soda, very strong acid. Bananas are a weaker acid, so it gets weaker as you get closer to the 7. Ammonia is a very strong base, but baking soda is a weak base because as it gets closer to the 7, it gets weaker, more neutral. Whenever your body has a strong acid or a strong base that it's exposed to, it has buffers. Buffers help to regulate the pH amounts. All right, so if you take a look at carbonic acid and bicarbonate, the bicarbonate is a buffer, and it's going to react with the carbonic acid. So in the case where we have a low pH, bicarbonate will join with that leftover hydrogen to make carbon dioxide and water. Whenever our pH is too high, the carbon dioxide and water can make carbonic acid and lower our pH. So that's the beginning of this chapter. It has a lot to do with inorganic chemistry. I hope that you enjoyed the video. See you next time.